1 and rule number 7 on left hand side, it will end up in this way: A small b, yes. So S goes to A capital B and capital B goes to small b, yes. So when I apply these two rules together, I'll get a derivation starting from S. S derives A, B, S, capital S. So now A and B has come. Now after S, I can have either B or A. Then come to the rule number 2. So now the whole 8 rules are defined in which way? See, for example, rule number 1 takes care of generating one A on the left with B on the right, and rule number 2 takes care of small b on the left with capital A on the right, and rule number 4 and rule number 7 produces, if A is there, it will produce one A and keep S in the production. And rule number 5 and 8 does what? A goes to, that is, if you apply the rule number 2 first, S goes to B capital A, and after that, after B again another B can come. Then in that case I have to go for rule number 5. If I apply rule number 2, S goes to BA. After B, I want another A here. Then I can go for rule number 4 or rule number 3. So now, that is, you start with one word A. After that, either A or B can come. After that, so for that reason, so S goes to AB, S goes to BA. This first two rules ensures the starting symbol as exclusive for the rule number 1 as A and rule number 2 as B. Okay, then what about the second symbol? Second symbol can also be B, either small b or small a actually. So now, so in S goes to B, so I want to have a B production. There are how many B production we have? Rule number 7 and 8 tells you that after A there will be one small b if there is a chance. Then it will take care of it will be taken care of by the rule 7. B goes to B, so that the first two symbols are A, B. After that I can have again A or B. If I want to have again A, then I can apply the rule number 1 again. So S goes to AB will take care of it. After that, I want to have any number of B's. Then I'll have this rule number 8. So B goes to A, B, B. So finally, in the nutshell of these 8 rules, I can have S goes to A capital B. That is, you just see the combination. Rule number 1, rule number rule number 1, rule number 7, rule number 8. This takes care of, in all these three, rule number 1, rule number 7, rule number 8, we have the concept, on the left hand side, on the right hand side, we have only B's. Along with B, on the left, there is A, there is a B, and on the right hand side, BB is there. So what is the role played by capital B here is, capital B will produce on small b. After that, it may be having, it will be suffixed by capital S or capital BB. In the same way, and this rule number 3 and rule number 6 for the termination. That is, S stands for the starting symbol, capital B stands for the generation of small b, and capital A stands for generating A. So with all this combination of 8 symbols, we'll have this any combination, any combination of A's and B, any combination of any words made up of A's and B's, such that the number of A's and number of B's are equal. A little amount of practice will make the things more clear. Then coming back to the another example. So now I want to generate A power n, B power n, C power n. So now G is equal to, the same way we are having NTPS, where n is equal to S and B and T is equal to. If I have what we did in the case of A power and B power n is ASB will generate, did the generation A power and B power n. In that sense, we are having this type of thing. S goes to ASB. So S goes to ABC. And here, instead of, the thing is, I can't maintain, I can't generate, I can't put the rules having only a single non-terminal on the right hand side. So I'm using CB is replaced by, in the context wise, it is replaced by BC, and BB is replaced by BB. Only then I'll be able to generate A power n, B power n, C power n, which tells you very clearly this language A power n, B power n, C power n is not a context free language. It is a context sensitive language. In the same way here, I want, if I have a rule, S goes to AS, S goes to BS, S goes to epsilon, then null word of length 0. Now, what is the language generated by these three rules, this grammar, where the non-terminals are S alone. So whenever the first rule is applied, A gets generated on the left. Whenever the second rule is applied, B will get generated on this. So now, in this, as first thing, by rule number 1, S derives AS, S derives ABS. Like that, when we make all this combination, we'll be getting all type of, all words that can be formed with the symbols of AB. So the language generated by this grammar is T star. In the same way, the grammar for WCW reversal, that is, the language given here is WCW reversal. We'll have one particular W here, and it is separated. After that we have a C, after the W reversal. For example, 10C01 will be an example for WCW reversal. So in that sense, what we have here is, when we have a what is the correlation between the W and W reversal? When you have the first symbol on W, that should be the last symbol in the W reversal actually. So in that combination, so far we were generating with the ASB, BSA, those things and all. And here S goes to A. See, the word, the symbol which comes in the first should come in the last. So there is a mapping pattern which is getting generated in the sense of WCW reversal. So S goes to ASA, will generate one A on the left, will generate one A on the right again. In the same way, S goes to BSB also will do it, and the C will do the purpose of the separating the W and W reversal. So S goes to C, it will terminate the whole derivation. So now WCW reversal will help in that generation. So this grammar S goes to ASA, S goes to BSB, and S goes to C collectively generate the language WCW reversal. In the another example of the grammar, W such that W is made up of left parenthesis, right parenthesis, and there is no epsilon in this. So W is a well-formed string of parentheses. So in that sense, in the same sense, how we derived here is S goes to SS, because here the well-formed string of parentheses means for every left parenthesis we should have a right parenthesis. So we are very much keen on putting the first rule. First production is S goes to SS. After that, S goes to left parenthesis, S right parenthesis, and the terminator is S goes to left parenthesis, right parenthesis. So this will take care of all these combinations here. So now, so if you have another example here is G, again the grammar is S alone. The starting symbol, the set of non-terminal is S, and the terminals are A comma B, and we have this S goes to SA, SBS, and this productions. The language generated by the grammar is the same as the language generated by this grammar. S goes to AB and other things. So after when two grammars are said to be equivalent, two grammars G1 and J2 are said to be equivalent if their respective languages are same. In fact, how to check whether the given languages are same? It's just a very simple, equality of two sets actually. So this tells you the equality of the grammar. And coming to the famous problem on palindromes. So if W is a palindrome, we want to generate a grammar. We want to design a grammar which will generate palindromes. And palindromes recursively define the palindromes as follows: epsilon, 0, 1 are palindromes. And if W is a palindrome, that is one, 1, 1 is a palindrome, 1 to 1 is a palindrome. That is, when you read from left to right and right to left, I should get the same word. So now CFG for the palindrome is getting generated by the rules S goes to 0, R1, R epsilon. Here this notation either, S goes to 0, S goes to 1, S goes to epsilon. We are collectively denoting with a single production. And here also S goes to 0, S0, 1, S1. The same what logic we applied for WCW reversal also the same thing. When the symbol which comes in the first should comes in the last. So S goes to 0, S0, or 1, S1. So now what, so far we have discussed about the context-free grammar, and then, we started the discussion with the motivation for the context-free grammar and the respective languages, and we defined the phrase structure grammar and gave out the classification of four types of grammar. Length increasing grammar, context sensitive grammar. Grammars like grammars for recursively enumerable language, context sensitive language, context free language, and the regular language. So we conclude this discussion on the context free grammar with this. In future lectures, we'll see how to simplify the context free grammar. Simplification in the sense how, the grammars which use minimum number of non-terminals to generate a particular languages, and the related normal forms and applications, everything. Thank you.